Have you ever heard of programming languages written in a grid? What? A programming language written in a grid? Yes. You heard that right, SPL, Structured Process Language. It is an open-source programming language written in a grid, specifically designed to handle structured data. Let's take a closer look below. SPL code written in a grid format benefits from natural alignment, with code blocks being simple and clear, due to natural indentation. In SPL, there is no need to define variables. Cell names can be used directly to reference the results of the corresponding cells. Additionally, when inserting or deleting rows and columns, cell names automatically adjust. For example, as illustrated here, after inserting a row, cell names automatically change without manual adjustment, which is highly convenient. SPL offers an intuitive IDE for development and debugging, featuring comprehensive functions like run, debug, run to cursor, step in, and breakpoints. Its step-by-step coding support allows you to view the calculation results of each cell in the results panel on the right, providing a clear and immediate understanding of the program's correctness. In addition to grid-style code, SPL offers option syntax, where similar functions use the same name are differentiated by options, simplifying memorization and usage. These options can also be combined for flexibility. SPL also introduced cascaded parameters, using semicolons, commas, and colons to separate parameter layers. This approach results in simple and clear statement expressions, eliminating the need for nesting and ensuring a unified statement structure. Grid-style code, option syntax, and cascaded parameters make SPL look fun, but its true purpose is efficient data processing. SPL, or Structured Process Language, is a low-code language designed specifically for handling structured data. There are many programming languages available for processing structured data today, such as commonly used SQL, Java, Python, and so on. Why to invent SPL? Because these codes are not yet low enough. That is, the code used to process structured data is not concise enough. Grouping and aggregation based on two fields is obviously cumbersome in Java, while SPL can get it done in just one line. Calculating the maximum consecutive rising days of stock in SQL requires 3 nested layers, not to mention writing. It may take a while to understand. In contrast, SPL can express the same computational logic in a single line. Even if you're not familiar with SPL syntax, you can still grasp most of the logic. Again, this task, Python doesn't convolute that much, but it still requires writing an explicit loop, resulting in a relatively verbose code. Conversely, SPL can achieve the same logic without needing loop statement at all, making it much more concise. Why are these languages cumbersome? This is due to their inability to simultaneously possess sufficient characteristics of set orientation and discreteness. What kind of thing is this? Let's explain using Java and SQL, the two languages with exactly opposite styles. Structured data is typically in bulk, meaning it's organized in sets. To facilitate the processing of such data, programming languages need to provide sufficient set computing capabilities. However, Java lacks sufficient set operation libraries, making these calculations cumbersome and often requiring extensive code. In contrast, SQL offers rich set operations, such as where for filtering, group by for grouping, and sum for aggregation, making it much simpler to write. Isn't it enough to add some library functions for set operations to Java? It's not that simple. Let's use sorting as an example. In SQL, you can simply write order by price to sort, without caring about the data type of price. Java is a type-strict compiled language, so the same function cannot work for different data types. This means you need to write separate sorting functions for integers, real numbers, and strings. It's not just a hassle for library function developers. Users also need to specify the data type, so the compiler can find the right function. Later, Java introduced generics, allowing functions to be written only once, but it can still look messy. Sorting can also involve multiple parameters. For example, in SQL, you can write order by price, quantity. You simply list the sorting parameters, and it works without any issues. But this is another issue for Java. Functions with varying numbers of parameters cannot be mixed, and the number of parameters is uncertain and cannot be exhaustive. Either use an array or combine multiple parameters into a single parameter, which is tedious anyway. SEQL doesn't have such an issue. Interpretive languages can dynamically decide how to do it based on data type and number. The thing is not finished yet. Sorting may also target an expression, such as using order by price times quantity in SEQL. This price times quantity needs to be calculated for each set member. Essentially, price times quantity is a function that takes the current set member as the parameter, meaning the function is used as a parameter. In Java, if an expression is written as a parameter to a function, it will be calculated before the call, rather than being calculated separately for set members. Java does allow functions to be passed as parameters, but it requires a more complex approach, which needs defining the function beforehand. Isn't it Lambda syntax that allows passing functions as parameters without defining them beforehand? Java now supports this. That's right. Java now supports Lambda syntax for defining anonymous functions as parameters. However, it cannot be written as a simple expression, otherwise, the compiler will evaluate it directly. Lambda syntax is similar to ordinary functions, in that it includes a function body, and even data types, except that it is not named. Additionally, due to frequent confusion between data types and the number of parameters mentioned earlier, the code can still become messy. SEQL makes Lambda syntax intangible, and no one even calls it Lambda syntax, but it does properly define functions as parameters using expressions. The issue with Java is that it cannot directly reference fields. Structured data isn't just a single value, but a record with fields. While SEQL only requires specifying a table name, when multiple fields share the same name, Java must use the verbose object.member notation. This is because Java's Lambda syntax doesn't naturally recognize records, it treats them as parameters, and accessing record fields requires using the dot operator. Only a syntax mechanism that allows direct referencing of fields can be considered truly professional for structured data computation. Java does not yet support dynamic data structures. In structured data computing, calculation often yields structured data that is related to operations and cannot be predetermined before coding. Therefore, the ability to support dynamic data structures is essential. Any select statement in SEQL can generate a new data structure, allowing fields to be added or removed freely in the code without needing to define the structure beforehand. Compiled languages like Java are not suitable for this purpose because all structures used must be defined before compilation. In principle, new structures cannot be dynamically generated during execution. Let's summarize. Set operation class libraries support dynamic types and numbers for parameters, intangible Lambda syntax allowing direct referencing fields of records, enabling dynamic data structure. These are what we commonly refer to as the set-oriented features of programming languages. With these features, processing batch structured data becomes more convenient. Interpreted languages like SEQL handle set-oriented features well, but compiled languages such as Java face challenges in this regard due to their inherent characteristics. This limitation is not unique to Java. Languages like Kotlin and Scala also struggle to fully support set-oriented features. After we've talked about Java, let's take a look at SEQL. As mentioned earlier, SEQL lacks discreteness, and its code is also not low. What is this discreteness? Let's take an example, calculating the median of a sequence. Structured data isn't necessary here. A simple array will do. This avoids hitting Java's soft spots, and prevents lengthy code from obscuring the key issues. As can be seen, Java often appears more concise than SEQL, when it does not involve structured data and Lambda syntax. On the surface, SEQL, as it does not directly support sequence number retrieval, can only create one separately. Even with window functions, the process can become quite convoluted. Java can easily retrieve members from arrays using sequence numbers for calculation, which is much simpler. The fundamental reason is actually the difference in data models between Java and SEQL. The data in high-level programming languages like Java is based on some atomic data that cannot be further split, such as numbers and strings. Atomic data can form more complex data such as sets and records, which are also some kind of data, and can also be combined into larger sets and records. The data that constitutes a set and record is independent of them, able to exist its own participate in calculations. Naturally, it provides the operation of disassembling members from the set and record, such as using sequence numbers and fields to retrieve members. This flexible form of data organization is called discreteness. By supporting discreteness, it becomes straightforward to construct sets of sets and records where field values are records. SEQL treats tables, which are sets of records, as atomic data rather than being composed of more basic data. SEQL data also lacks composability. Tables are the smallest units, and records cannot exist independently of tables. A single record is essentially a table with just one record. This makes SEQL's data organization very inflexible, that is, lacking in discreteness. Lack of discreteness can be cumbersome when implementing calculations. For instance, to list employees whose age and income exceed John's, one would typically write in SEQL statement that first identifies John's record, and then uses it for conditional filtering. But this SEQL statement is illegal. The second half of the statement requires using join, which can be a bit convoluted. This highlights the difference between tables and records in SEQL, as there is no data type that can directly hold records. Java's support for set operations on structured data is limited, so we switched to SPL for its superior set-oriented capabilities. This is the natural approach. Let's look back at the example of calculating the number of consecutive rising days of a stock earlier. The ordered computation involved here is a typical combination of discreteness and set orientation, where the order of members is meaningful only in the set. This requires set orientation, and in ordered computation, each member must be distinguished from adjacent members, emphasizing discreteness. Discreteness enables more thorough set orientation, and conversely, set orientation allows discreteness to play a broader role. SEQL lacks discreteness and its set orientation is not thorough, ultimately leading to convoluted and hard-to-read code. Set orientation is a syntactic form reflecting code complexity, while discreteness is a data model that reflects the difficulty of the code. Java code lacking set orientation can become very complex, whereas SEQL code without discreteness might be shorter, but convoluted and harder to manage. That's why the code in Java and SEQL is not low. How about Python? As we discussed earlier, SEQL and Java have notable shortcomings in terms of discreteness or set orientation, resulting in poor overall effectiveness. While Python has greatly improved in these two aspects, but it's still not good enough, and tasks such as ordered computations are still cumbersome. Our goal is to emphasize both set orientation and discreteness to enhance overall capability. In fact, from the previous discussion, we can easily conclude that to achieve low-code solutions, we just need to effectively combine Java's discreteness with SEQL's set orientation. This was the original intent behind creating SPL, a low-code programming language designed for structured computing, to better integrate set orientation and discreteness. SPL inherits the advantages of both Java and SEQL, providing more thorough set orientation and embodying the characteristics of a low-code programming language. Compared to other structured data processing languages, SPL has more comprehensive and outstanding capabilities. Looking back at the example of calculating the longest consecutive rising days of a stock, let's take a look at the syntax style of SPL. The expression of loop functions that support ordered computation and strong lambda syntax is very concise, without the need for loop statements, let alone nesting, and can be written in a single statement. There is also an actual case of e-commerce funnel calculation, where SPL is not only written simply, but the program is also more versatile and can handle any step of funnel calculation, all of which are benefits brought by the low-code feature. Let's then talk about performance. Data processing involves two key issues: writing simple and running fast. We know that software cannot speed up the hardware. The CPU and hard disk have fixed speeds. However, by designing low-complexity algorithms that require less computation, the computer would perform fewer actions, leading to faster execution. Algorithms need not only to be designed but also to be implemented. This means that low-complexity algorithms should be easy to implement to ensure they are practical. From this perspective, simplicity in writing and speed in execution are essentially the same thing. SPL has low-code characteristics, making it easy to implement low-complexity algorithms and achieve high performance. In contrast, Java and SQL often struggle to implement the same algorithm, with some being impossible to achieve, leading to ultimately lower performance. SPL has many optimization cases for database SQL, often achieving tens of times performance improvement. The reason is here. Low-code SPL is now open source. Welcome everyone to download and try.